This is the first video that goes with Chapter 12, Differentiation, and in this video we're going to discuss what is differentiation, how do we do differentiation from first principles, and what is the basic rule for differentiation. So first of all, differentiation. Basically, differentiation is finding the gradient of a curve. Differentiation gives us lots of information about rates of change. So when we're doing rates of change, we need the gradient of the curve. So let's have a look. So first of all, I need a curve. So I'm going to draw a curve. Here's a curve, there's a curve. And I'm going to call that curve y equals f of x. This is any curve. And I'm going to pick a point on that curve. I'm going to mark it in red. So this is point A. And of course, if I wanted to measure the gradient of point A, I would put on a tangent. So I'm going to put a tangent that goes through point A. There it is, tangent at point A. Now, if I wanted to measure the gradient of that tangent, what I could do is put on a gradient triangle. Unfortunately, that wouldn't be accurate because I'm measuring the vertical and the horizontal. So there must be a more accurate way of doing it. So what we can do in maths, what I can do is I can pick another point. So I'm going to pick another point and I'm going to pick a point that's quite close to A. And I'm going to pick point B. And there it is, quite close to A. Now, the horizontal distance between A and B I'm going to call H. There it is. So, because I'm working, I want the gradient at A. The coordinate at A is x, f of x. Of course, the coordinate at B, so I've gone vertically across H, the coordinate will be x plus h and f of x plus h. So the vertical distance from A to B will be f of x plus h minus f of x. So the gradient between A and B is going to be f of x plus h minus f of x divided by h. In other words, change in y over change in x. And that will be represented by the gradient of this line. In fact, I'll do it in a different colour so it really stands out. I'll do it in purple. There it is. So the gradient between A and B is very similar to the gradient at A, but it's not perfect. So how could I make it better? Well, what I could do is I could move B closer to A. So I'm going to do that one in green. So I'm going to move B to here. So it's closer. The coordinate for B would still be x plus h because I now am making h smaller. This is now h from here to here, and this is the vertical distance. I'm making h smaller, and of course the gradient of the line between A and the new point of B will be a better approximation of the gradient at A, but it's still not good enough. In order to make it better, I could move the point closer to A. In other words, I'm making the value for h smaller and smaller and smaller to the point where it's so small that it's almost touching A. And in maths, we say that what's happening there is h is tending to 0. It doesn't become 0, but it tends to 0. So have a little look. So the gradient function, or sometimes refer to it as the derivative of the curve y equals f of x, is written as f dash of x or dy dx. Now, f dash of x is what we use if we started with our original function in function notation, and this is referred to as Lagrange notation, f dash of x. And if we've started with y equals, and that is Cartesian notation, we end up with dy dx, which is Leibniz notation. And from above, we end up with this equation, this formula. And the formula is f dash of x equals the limit as h tends to 0. Remember, we wanted to make h smaller and smaller and smaller, so that's the limit as h tends to 0 of f of x plus h minus f of x, that's your change in your y's, over h, which is change in the x's. Now, that formula for differentiation by first principles or from first principles is in the formula book. You don't have to remember it, but you do have to have some idea of where it's come from and how to use it. So we're going to look at how we use it. So our first example says, prove from first principles. That gives you an idea that you're going to be using the first principles formula, that the derivative of x cubed is our function, is 3x squared, and that's our final answer. So we're going to start setting it up. So the first thing, our function, f of x, is x cubed. And of course, if you remember, the formula's got f of x plus h in it, so we need f of x plus h, which is x plus h, all cubed. I'm now going to write the formula down. So it's f dash of x equals the limit as h tends to 0 of f of x plus h minus f of x over h. We're now going to put in what we know. I'm not going to write the f dash of x down the left-hand side, but I am going to write the limit as h tends to 0. F of x plus h, of course, is x plus h all cubed. F of x was x cubed, so that goes on the end, divided by h. We're now going to expand, so we get the limit as h tends to 0 of, and it's x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed divided by h. Now what you'll notice is the x cubed cancel each other out because you've got x cubed minus x cubed. And for the next line, I'm going to pull out h as a common factor from the numerator. So we've got the limit as h tends to 0, pulling out h as a common factor, so I get 3x squared plus 3x h plus h squared all over h. And then you notice that the h that we pulled out as a common factor and the h in the denominator cancel each other out. So we've now got the limit as h tends to 0 of 3x squared plus 3x h plus h squared. Now, as h is tending to 0, 3xh will also tend to 0, because it doesn't matter what x is, because h is becoming very small and smaller and smaller, it's going to tend to 0, and h squared will tend to 0. So these two terms, this one and this one, will, as h tends to 0, also tend to 0, leaving me just the 3x squared term, so therefore f dash of x equals 3x squared, which is what I was asked to prove. Now let's look at how we can do this one with a few numbers in it. So we've got a question here. It says the point A with coordinates 4, 16 lies on the curve with equation y equals x squared. At point A, the curve has gradient g. So this is my x value. Y equals x squared is the function we're working on, and it says we've got a gradient of g. And we're asked to show that g equals the limit as h tends to 0 of 8 plus h, and part B, deduce the value of g. So we're going to start writing a few things out. Now, first of all, we know that our function of x is x squared. We also know that x is 4, so f of 4 will be 16. If you remember, in the formula, we need f of x plus h, and that will be x plus h squared, and of course x is 4, so f of 4 plus h will equal 4 plus h all squared. Now I'm going to write the formula out. So f dash of x equals the limit as h tends to 0 of f of x plus h minus f of x over h. Now, f dash of x is the gradient. F dash of x equals g. We're told here the gradient of g. So g equals the limit as h tends to 0. F of x plus h is x plus h whole squared. We know that x is 4, so this is 4 plus h whole squared minus f of x, x squared, when x is 4, that gives us 16, divided by h. G equals the limit as h tends to 0, and we're going to expand, so we get 16 plus 8h plus h squared minus 16 over h. As before, 16s will cancel, and I'm going to pull out h as a common factor from the numerator. So we'll get the limit as h tends to 0 of h bracket 8 plus h over h. Again, these h's cancel, and what are we left with? We're left with g equals, or therefore g equals the limit as h tends to 0 of 8 plus h, which is what I was asked to prove. Now, part B, we'll do it on the right hand side here. It says deduce the value of g. Well, you can see as h tends to 0, g will equal 8, because here h will tend to 0. Now, so that is differentiation from first principles. Now, if we just have a little look, I'm just going to write a few things down. Now, if you look in part A, we said that if y was x cubed, we proved from first principles that dy dx, or f dash of x, was 3x squared. Again, I could have done 2x to the power 5, take me a little bit longer, but I would have got dy dx equals 10x to the power 4. I could have done y equals 3x to the power 4, and from first principles I would have proved that that was 12x cubed. Now, if you have a little look at those, you should see a pattern. First of all, you should notice that what happens, the power decreases by 1, and also you will notice that the coefficient of x in the derived function, the gradient function, is the product of the coefficient and the original power, and that is true. So when we do first derivatives, in general, the gradient function of a curve y equals f of x in the form, and this is quite important, it must be in the form kx to the power n, or you can have ax to the power n, completely up to you, is given by the derivative dy dx, which is equal to f dash of x, depending what form you're in, and it's kn x to the power n minus 1. So in words, what we do is we multiply the power by the coefficient, and then we decrease the power by 1. And that is the basic rule for differentiation. So we multiply the power by the coefficient, and then we decrease the power by 1. Equations relating functions and their derivatives are referred to as differential equations. So we are now going to practice that in the two forms, function form and Cartesian form. So we've got some examples here. Now we're going to start with function form. So we're going to go f dash of x, which is, remember, is Lagrange notation. So the first one, f dash of x equals 7x cubed. So f dash of x equals, multiply the power by the coefficient, so we get 21, and then we reduce the power by 1, and that is our gradient function, often referred to as the gradient function. The next one, remember, it must be in the form ax to the power n or kx to the power n, and this one is, so b. So we get f dash of x, I'll just repeat that, f dash of x equals, so multiply the power by the coefficient, so we get -8, and reduce the power by 1, so we get -3. Be careful, you don't want to add 1 to the power, you need to take 1 from the power. Now if you look at C, you will notice that isn't in the form ax to the power n or kx to the power n, so we have to simplify it first before we do anything, and we often simplify using our indices rules. So f of x equals, so 2x cubed divided by x squared is 2x, and remember that's power 1. Okay, so f dash of x, multiply the power by the coefficient, so we get 2, and then it's x to the power 0. Now you know from your work at GCSE that x to the power 0 is 1, so that actually equals 2. So what you should be noticing is that cubics become quadratics, quadratics become linear, and a linear will become a constant. So the question is, in part D, what happens to constants? Well, here f of x equals 4. I can't really apply the rule, multiply the power by the coefficient, because I haven't got a power. But what I'm going to do is I'm going to write x to the power 0. Now remember, x to the power 0 is 1, and therefore that's not changed the term. And then I can apply my rule. So f dash of x equals, multiply the power by the coefficient. Well, 4 times 0 is 0, and then reduce the power by 1, so this gives us x to the -1. Remember, that is 0 over x, and anything divided, 0 divided by anything is 0. So in other words, f dash of x equals 0. So quite important, this one, that a constant value will become 0 when you differentiate it. Now let's have a look at E. So you've got f dash of x equals the square root of 9x cubed. So the first thing we're going to do is we're going to say that's 9x cubed to the power a half. Then we're going to apply our index rules. So f of x equals 9 to the power a half is the same as the square root of 9, which is 3. And x cubed all to the power half is x to the 3 over 2. And then we can differentiate it. So multiply the power by the coefficient, so we get 9 over 2x, and decrease the power by 1, so you get x to the power half. And you could, if you wanted, write that as 9 over 2 times the square root of x. Either of those is acceptable. So those were all given in function notation. Now question 2, these are given in Cartesian notation. So we are going to be finding dy dx, so we're going into Leibniz form. The first thing we've got to do is we've got to simplify each of these. So first of all, we're going to simplify. So 4x squared times 3x to the power 5 will be 12x to the power 7. Remember, multiply and add your powers. So dy dx equals 12 times 7 is 84, x to the power 6. Part B, we just simplify that. So if you simplify the top, you get 10x to the power 8. So the numerator is 10x to the power 8. Denominator is 5x to the power 12. If you simplify that, 10 divided by 5 is 2. X to the power 8 divided by x to the power 12 is x to the negative 4. And then you can differentiate it because it's in the form ax to the power n or kx to the power n. So you're going to get negative 8x to the negative 5. So what you are doing here is you are finding the gradient function. So dy dx equals negative 8x to the negative 5. That is the gradient function. Now let's have a look at y, at c. Again, we need to simplify this one. So we're going to apply the negative 1/2 power. So we've got y equals, it's 16 to the negative 1/2 times x to the negative 5/2. And 16 to the negative 1/2, of course, is 1 over the square root of 16, which is 1/4, x to the negative 5/2. So dy dx is multiply the power by the coefficient, so I'm going to get negative 5 over 8x. And if we take 1 from negative 5/2, we get negative 7/2. And again, that is the gradient function. Now there are some terms we have to be really quite careful with. So number 3, we've got 3 over x. Again, that has to be in the form kx to the power n. So that's 3x to the negative 1. And then we're going to differentiate that. So we get negative 3x to the negative 2. Or you can write that as negative 3 over x squared if you want to. Now number 4, be very careful with number 4. When you simplify it, you are lifting the x, not the 3. So y equals 2/3 x to the negative 1. Then you can differentiate. So dy dx equals negative 2/3 x to the negative 2. Or of course that's the same as negative 2/3. And then your x squared will be at the bottom, negative 2 over 3x squared. Again, look at number 5. Be very careful. We're going to simplify this. I'm going to do it in steps. So this is 1 over 8x cubed, because 2 to the power 3 is 8 and x to the power 3 is x cubed. Then we need to just lift the x cubed, so that will be x to the negative 3. And then we can differentiate it. Multiply the power by the coefficient, so we get negative 3 over 8, and negative 3/8 x to the negative 4. And again, you could write that as negative 3 over 8x to the power 4. The 6th one again, number 6, I'm going to write this as 6x to the negative 1/2. And then we differentiate. So dy dx equals, and that's going to be minus 3 or negative 3x, negative 3 over 2. Okay, or of course, what that one is negative 3 over, and this is the square root of x cubed. Either of those would be acceptable. Now, sometimes we are asked to find the actual value of the gradient, and if we want to do that, when we've found the gradient function, we need to put the value of x in. So we're going to have a little look at that. So the first question says, find the gradient at x equals 4 on the curve y equals 4x to the 3 over 2. So again, information, first of all, you can see the word gradient. When you see the word gradient, you're not always asked to do dy dx. You see gradient, that tells you you're going to be differentiating. You're given your curve. So y equals 4x to the 3 over 2. So first of all, dy dx equals multiply. So 4 times 3 over 2 is 12 over 2, which is 6x. Decrease, so that gives you power a half. Okay, so that's the gradient function. That is the gradient everywhere along that graph. We want it at a specific place, and you can write dy dx line, and then x equals 4. That tells us that we're looking at a specific point on that graph, and that will equal 6, and that's 4 to the power a half. Therefore, dy dx when x equals 4, that is 12. So the value of the gradient is 12. Okay, and this one, this is given in function notation. This is Lagrange, so it says find f dash of x when x equals -2. Remember, that's what that means, given that f of x equals 5x cubed. So if f of x equals 5x cubed, then f dash of x equals 15x squared. Multiply the power by the coefficient and decrease the power by 1. Therefore, f dash of -2 equals 15 times -2 squared. And of course, f dash of -2 will equal 60. So that's the value. Now, we can differentiate a function that's got more than one term. So it's if f of x is made up from terms, so g of x plus h of x, then f dash of x is g dash of x plus h dash of x. That's just saying that if a function is made up from multiple terms, as long as each of those terms is in the form ax to the power n or kx to the power n, we can differentiate it. So it says find dy dx. There's the clue that we are differentiating, given that y equals each of these expressions. So I'm going to start y equals x squared plus 3x. Therefore, dy dx equals, to differentiate this, we get 2x to the power 1. There's no point in writing power 1. And 3x becomes just 3. Okay, because you get 3x to the power 0, of course, that just is 3. Next one, y equals 8x minus 7. So dy dx equals 8. Okay, remember, minus 7, when you differentiate it, it will become 0, so there's no point in writing it down. Next one, again, I'm going to write y equals 4x squared minus 3x plus 5. Therefore, dy dx equals, and this is 8x minus 3. Again, multiply the power by the coefficient and decrease the power by 1. And of course, the plus 5 just becomes 0. D, I've got y equals 4x cubed plus 2x. Therefore, dy dx equals, that will be 12x squared plus 2. E, again, y equals x cubed plus x squared minus x to the power half. So dy dx equals, multiply the power by the coefficient and decrease the power by 1, so you get 3x squared plus 2x minus a half x to the negative a half. And again, you could write that last term in third form if you wanted to. And f, we've got y equals a third x to the half plus 4x squared. Therefore, dy dx equals a 6x to the negative a half plus 8x. So if you have a little look at that, that's should start to become quite formulaic. Again, with these, just have a little look at these last two. We'd be asked to differentiate that. Now, just be very careful. You'll notice in question 1, I didn't write, look at E, and I'll do it in red. It was x cubed plus x squared minus x to the half. I didn't just put equals 3x squared plus 2x minus a half, x to the negative a half, because it doesn't. We've got to be very careful in maths when we're writing things down, so that's actually not true. So we've got to start and make sure that everything we write down is true. So it says differentiate 1 over 4 root x. So I'm going to write y equals a quarter x to the negative a half, because I've just simplified that term so we can differentiate it. And then we're going to differentiate, therefore dy dx equals negative an eighth x to the negative 3 over 2. Okay. B, before we start, we're going to multiply that out. So we've got 3x to the power 4 plus x cubed. Therefore, dy dx will equal 12x cubed plus 3x squared. And the last one, again, we're just going to simplify that. We're going to let y equal x minus 2 over x squared. So we're going to simplify that. X divided by x squared, of course, is x to the negative 1, and that's minus 2x to the negative 2. And we're going to differentiate that. So we're going to get dy dx equals, and it's negative x to the negative 2, then plus 4x to the negative 3, then multiply and decrease. So what you need to do now, in order to practice this, you need to have a go at the following. Exercise 12b, questions 5 to 7, and that's using differentiation from first principles. And then exercise 12c and 12d, which are all using the basic rule for differentiation, remember, which is multiply the power by the coefficient, decrease the power by 1, but each term must be in the form kx to the power n. So make sure you put every term like